when we start looking at the properties of different functions, there are two very exclusive clubs that a function can end up being a part of. It can be what we call an even function, or it can be an odd function. Now don't get this confused with the idea of even degree polynomial and odd degree. These are much more exclusive clubs. It's a little hard to see up here, but VIP, they're exclusive. There's only one way into the club of being an even function, and one way into the club of being an odd function. And most of us are going to end up being what we call neither even nor odd. So we're just looking to see, are the functions that we're dealing with special enough to be considered even or odd? In order to be considered an even function, we have to have symmetry with respect to the y-axis. If that exists, then we are considered an even function. The most famous example of an even function, or the easiest one for us to look at, is x squared. If we just sketch his graph, we know that he is symmetric to the y-axis. Therefore, we're going to call him an even function. He is also an even degree polynomial, but he's an even function, which is a more exclusive club than even degree polynomial. For an odd function, we have symmetry with respect to the origin. If that exists, then we consider it to be an odd function. So the example I always go to is x to the third. He has symmetry with respect to the origin. I just remember origin is odd, origin odd. That's the easy way for me to remember. There's a couple other parent graphs that are odd functions. For example, x. We talked about the cubed root of x. Those are also odd functions. They have symmetry with respect to the origin. And then there's the category that we call neither. And that's where most graphs are going to end up. Neither just means I don't have either of these types of symmetries. So for example, something like x minus 2 squared. If we remember what he looks like, he's moved 2 to the right. He is going to be neither even nor odd. He's not exclusive enough to join one of those two clubs. He's just a graph. Or something like f of x equals third root of x minus 4. If I look at that, it's going to be down here, my normal third root. He doesn't have either of those types of symmetries, so we're going to say that he is neither even nor odd. Most functions fall into the category of neither. Some exclusive ones do fall into the odd or even category. So if we have a graph, it's not that hard to look at the graph and get a good idea of whether or not it's an even, odd, or neither function. If we have just the equation, it's a little bit trickier. So algebraically, if I want to find if something is even, if I replace every x with negative x, I do the math, in other words, simplify, and I get back the original function. Which makes sense if you think about the graph here. Every x value and every negative x, the opposite of that value, have the same output. I can't distinguish between their outputs. So down here, I'm replacing every x with negative x. I'm looking at all the opposites and seeing, do I get my original y values back out? Another way of saying it is f of negative x equals f of x, which is just a mathematical way of saying what that sentence says right there. So if I look at my first example, f of negative x equals, I'm going to replace every x with negative x, which is just that one value. I'm going to look at what's the squared do. I know that squareds go ahead and make negative signs go away because I'm squaring to negative 1. So I get back to 3x squared minus 8, which is the same as the original. If it's the same as the original, so that guy and that guy are the same, then I can say that it is an even function. He happens to also be an even degree polynomial, but more specifically, more exclusively, he's an even function. Same thing down here with example 2. I'm going to look at replacing every x with negative x. So this becomes 1 over negative x to the 4th minus 3 times negative x squared. I know that even powers make the negatives go away. So that's 1 over x to the 4th minus 3x squared, which again is exactly what I started with. So these two things here are the same. When they're the same, I know that I have an even function. Notice this one is not an even degree polynomial because of the 1 over x to the 4th, but he's still an even function. There's a little bit you can do by looking at exponents to see if it's an even function or not. If you have all even exponents, that's one way of looking at it. But you have to be careful because something like this, that 8 does have an x to the 0 power, so it works in that case. But it can get a little bit tricky. It's better just to plug in the negative x and see what happens. In terms of odd functions, if I replace every x with a negative x, I do the math, and then I get back the opposite of the original function. So I'm looking at the opposite of the original function. In other words, every sign, S-I-G-N, every sign changes. Which makes sense. If I look up here at my picture, here I have an x and some sort of y value. And if I look what happens when I apply origin symmetry, when I go to the opposite of x, I have the opposite of y. Everything changes when I plug in that negative x. So I come over and take f of x. I'm going to do f of negative x. And that's going to be negative 2 times negative x to the 5th plus 3 times negative x. Now I know that when I raise negatives to odd powers, I can imagine that they come out front, and they come out front. So this is going to be 2x to the 5th minus 3x. So in this case, if I look at my original and my final, my original right here, I had a negative that turned to a positive 2x, positive that turned to a negative 3x. Every sign changed, so this is an odd function. It's part of that exclusive club. If I were to graph it, it would have origin symmetry. I forgot to write up here the mathematical way of writing the f of negative x equals every sign changing means I have negative f of x, or the opposite of my original. So that's just a mathematical way of writing that. But the key is just to remember that every sign changes. So example 4, f of negative x is going to be the third root of negative x plus 1 over negative x. I know that negatives come out of third roots, and this negative can come up. So he's going to equal the negative third root of x minus 1 over x. And again, if I look at it, every sign changes. This positive here became a negative down there, and this positive there became a negative right there. So that is going to convince me that this is an odd function. He's just part of that club. If we were to graph him, he would have symmetry with respect to the origin. So there's even and odd. Example 5, when I look at that one, I'm not sure just by looking at it. I have a guess that since there's a mixture of odd and even exponents, that it's going to be neither even nor odd. I don't know what his graph looks like without actually doing a little bit of factoring and sketching it out. But I can check and see what happens with f of negative x. So that's going to be 4 times negative x to the third plus 2 times negative x squared. So in the first case, this negative comes out. So this is negative 4x to the third. But in the second case, the negative goes away. So that's plus 2x squared. So not all the signs changed, and not all of them stayed the same. So not all sine to g changed or stayed the same. That's why it is going to be neither even nor odd. If you were to graph this function, you would find that it does not have symmetry with respect to the origin or symmetry with respect to the y-axis. So when I'm looking at my different exclusive clubs, For even functions, y-axis symmetry, or I get back the original when I put in negative x. For the odd functions, it's origin symmetry, or I get back the opposite whenever I plug in negative x. And then neither is just everybody else, which is the category that most things would end up falling into.